Hi everyone. Today we'll understand why functions that have a positive derivative on an interval are increasing on that interval. We'll use the mean value theorem for that. In the first exercise, we must recall what the mean value theorem says. If you would like to try this exercise on your own, stop the video now. You can also download these notes using the link in the video description. The mean value theorem says that if f is a function on the interval ab, such that f is continuous on the interval from a to b, a and b included, and f is differentiable on an interval ab, a and b not included, these are the two assumptions of the mean value theorem, then there exists at least one c in the interval from a to b, a and b not included, such that the value of the derivative at that c equals f of b minus f of a divided by b minus a. And that quantity on the right side represents the average rate of change of the function f on the interval ab. Let's see if we can apply the mean value theorem to show that if a function has a positive derivative on an interval, then that function is increasing on that interval. Ask yourself, what does it mean that a function is increasing on an interval ab? Let's visualize this. Here is the y-axis. Here is the x-axis. On the x-axis, we have two numbers, a and b. What does it mean that the function is increasing between a and b? I believe that means the following. If I choose any 2 points between a and b, for example, this point and this point, let's give those points names. Let's call it x1 and x2. No matter which 2 points I choose between a and b, the function will be increasing if the value of the function at x1 is less than the value of the function at x2, where x1 and x2 are arbitrary 2 points between a and b, such that x1 is less than x2. Because that way, the function will be increasing. If the value at x2 was less than the value of the function at x1, then that function would not be increasing. My goal then is to choose any 2 points between a and b and show that if x1 is less than x2, then the value of the function at x1 is less than the value of the function at x2. What I'm assuming then is that I have points x1 and x2 such that x1 is less than x2. What's more, both x1 and x2 come from within the interval ab. I can assume one more thing. I can also assume that the derivative inside of the interval ab is greater than 0. And I can assume that because that is what the question said. Prove that when the derivative is positive, the function is increasing. I'm assuming the fact that the derivative is positive, and I will prove that the function is increasing. These two I can assume. Both of these hold on the interval ab. I have 2 points from ab, and the derivative is greater than 0 in the interval ab. What I need is I need to show that f of x1 is less than f of x2. That will show that the function is increasing. The value at the second point is larger than the value at the first point. I would like to prove it using the mean value theorem. However, to use mean value theorem, I need to know that the assumptions of the mean value theorem are satisfied. The assumptions are that the function is continuous and differentiable. And I would like to use the mean value theorem on the interval from x1 to x2. Do I know that the function f is both continuous and differentiable on this interval? Continuous on a closed interval and differentiable on an open interval. And I believe this is true. Note that we can assume that the derivative is greater than 0, we know that the derivative is greater than 0. In particular, this implies that the derivative exists. To be greater than 0, the derivative must exist. So this means that f prime exists, which is the same thing as saying this function is differentiable. This function is differentiable everywhere here, which means it's differentiable, the derivative exists in the interval from z1 or x1 to x2. We also have a theorem that says that if a function is differentiable, the derivative exists, then the function must be continuous. That means that this also implies that f is continuous on the interval from x1 to x2, x1 and x2 included, because this function is differentiable everywhere between a and b, which means it's continuous everywhere between a and b, which means it's definitely continuous between x1 and x2, including x1 and x2. The two conditions of the mean value theorem are satisfied. This means that the conclusion of the mean value theorem follows. This means there exists, by the mean value theorem, MVT, there exists C in the interval from x1 to x2 such that f prime of C equals f of x2 minus f of x1 divided by x2 minus x1. Instead of writing the conclusion of the mean value theorem this way, let me first multiply both sides of this equation by x2 minus x1, to multiply both sides of this equation by the denominator of this fraction. When I do that, I will get f prime of C times x2 minus x1 equals f of x2 minus f of x1. And I know it's hard to believe it, but we are almost there. We just have to notice two more things. The quantity x2 minus x1 is a positive number, and that is because x2 is bigger than x1. We assume that x2 is bigger than x1. So when you do x2 minus x1, you get a positive number. What's more, f prime of C is also a positive number, and that is because we said that the derivative is always positive, which means no matter what you plug in between a and b, you always get a positive number. So when you plug in C, which is somewhere between x1 and x2, you will get a positive number. This number is positive, this number is positive. Multiplication of two numbers that are positive gives you a positive number. Consequently, this expression on the right side is also a positive number. This is greater than 0. Now you have an inequality. Add f of x1 on both sides of this inequality, and you will get f of x2 is greater than f of x1, which is exactly what you wanted to prove. You just showed that if a function has a positive derivative on an interval, then that function is increasing on that interval. You showed the first part of the following theorem. If the derivative of a function is positive on an interval, then that function is increasing on that interval. Using the same idea, you could also show that if the derivative is negative on an interval, then the function is decreasing on that interval.